Hi, I'm Akash,
I'm Isha.
and today we're going to be joined by our co-authors on a recent paper on inference time scaling. If you haven't heard about it yet, well, I'm genuinely disappointed in our social media skills, but don't worry, a link to the work will be somewhere in the description depending on where you're watching this. So why are we here today? Well, Isha recently presented this work in one of our seminar series, and we got a ton of interesting questions. What stood out was the sheer number of questions on the broader impact of this technology, specifically how inference time scaling and reasoning model will shape the LLM deployments in business and enterprise setting. Now, it might sound a little bit like, why are people interested in this?
Yeah.
But, this is the DeepSeek effect.
Yeah.
That model has really made people who are thinking of investing in AI to bring that AI into their business, or people who already invested in and have certain models on-prem, they want to make sure that they made the right decision.
Yeah.
So we thought, why not bring the whole team of experts back and tackle some of these questions in a more relaxed environment where we can, chat and, if necessary, even speculate, give our opinions. So without further ado, let's jump right with our first question.
Let's go.
Okay, Isha, so let's do some level setting, right? As your catchphrase goes, no math.
Yes.
Could you explain to us what is inference time scaling and reasoning in the context of large language models?
Yeah, absolutely. So I think, as a lot of people who are watching this or listening to this probably know, and a lot of people across the world know, I think language models have over the last few years made a giant splash in the world just because of how useful they are. They have a variety of capabilities. You can use them to do, as you said, math reasoning problems. You can do recipes. You can do homework, as a lot of children across America know. I think they have a variety of applications that are very useful to people. But there are some drawbacks that come from using them and don't necessarily make them accessible to everyone who could use them. So I think one of the drawbacks, as everyone knows, is that they are kind of hidden behind an API wall. So in order to use these applications, in order to use these language models, you do need to send your data to this closed source entity. You want to send your data to OpenAI, to Anthropic. And this is not necessarily accessible to a lot of people, both for preference. I don't want to send my data if I'm a sensitive enterprise, but also I might not be allowed to send the data because of healthcare regulations or education or a lot of those fields, which means that there's entire groups of people and enterprises that are not getting access to the powers of language models just because, it's not set up for them to be able to be used. And the other kind of drawback is, a thing that most enterprises care about, which is cost. And both energy-wise and monetarily, it takes an extraordinary amount of compute, an extraordinary amount of money to train these language models at a scale where they'll be useful to a wide variety of people. So I think this is why people kind of care about open source language models, is because they're smaller, they're easier to train, and if you can get them to be useful in whatever workflow you have, and if you can actually get them to be working, it would be fantastic. Which is where this kind of interest in inference scaling comes in, because you want to be able to get open source language models to be useful in your workflow. But how do you actually do that? And I think this is where this entire field has kind of captured the interest of a lot of people in the community, where the question kind of then becomes, if I have a smaller open source language model that objectively doesn't have the one-shot immediate performance of GPT-4 or GPT-01, how can I most intelligently sample or query this language model to kind of squeeze all of the juice out of it, to kind of get it to almost hit above its weight class in terms of how it performs? And so the question becomes I have this language model. I'm not just going to query it once. If I gave you 64 or 128 chances to ask this language model a question, how can you most intelligently ask the questions? How can you guide its search process to get it to create, answers that are better than what it typically would? So I think, Shiva's going to touch on this later, but in terms of if I had to ask you, how are you going to most, interestingly make use of your 64 language model queries, you could kind of think of this as a metaphor in terms of what a lot of people have done in school or in math classes, where your teacher gives you a group project or a group, you're in groups and they give you a math problem and you have to just kind of figure out how to work together. So there's a bunch of different ways you can do that, right? You can kind of have every single person do their question individually, and you just pick, okay, at the end, which one do most of us agree with? And we'll just go with that. And there's also, if you are, you happen to have a tutor with you or an older student or someone who's super cracked at math, you have them kind of help you with this. So everyone comes up with an answer And then this tutor is like, hey, this one looks the best, so I'm actually going to choose this answer. Or if you have a tutor who's kind of watching you as you're doing your process of generating this question, you do step 1 of the math problem, it's looking great. You do step 2, it's looking great. You do step 3, and you make a mistake. The tutor's like, actually, you know what? I think step 3 looks wrong. Do you want to go back and try that again? And I think what inference scaling is this overall field of like, how do I, given this very small language model that maybe at first glance doesn't have the capabilities that a larger, more advanced model would, how can I more intelligently sample it to get it to that level? And I think what's interesting about this is that, work like ours that we'll touch on later, and then also, a lot of people who are working on this have been able to get results that, with like a 7 billion parameter language model, which in the grand scheme of things is minuscule in terms of like training and all this stuff, is able to actually get to a GPT-o1 performance in like 64 rollouts or 64 queries with no additional training, which I think like makes it incredibly accessible to people who want to use it, both from a cost perspective and a privacy perspective, but also if you have your own small customizable language models and you want to fit them into your pipeline, trying to find a way to like just use that, I think inference scaling makes that possible. And to touch on the reasoning part of this, I think reasoning, as kind of going with this math metaphor that a lot of people can relate to, I think reasoning is not just about having a question and answer. You want to find the most logical way to get there. And I think reasoning in language models and open source language models is about trying to get them to think longer and harder about questions, and kind of having a very reasonable step-by-step process where you can think your way around questions. And getting smaller language models to do that is more difficult because, they just don't have the capabilities out of the box sometimes. But inference scaling and a lot of techniques that we'll probably touch on later allow this to happen, where you can get a language model just perform at a level that is higher than it's initially gifted with.
Awesome. I really love the example you gave of kids working on a math problem.
Yeah.
Really connects to like how these algorithms actually work. And talking about these algorithms, let's go to Shiv. And Shiv, like, could you walk us through, if I were to sort of pick what a technology in inference time scaling, or test time compute as it is sometimes called, what are my options?
Right. So let's start with a simple technique. It's called best of n. So if you've used ChatGPT before, you might have seen the try again or the regenerate button. So what it basically does is if you click on it, it's going to give you a new response. And what you do is you keep doing it until you find an answer, which are pieces here.
Right.
So in this case, you are what we call a reward model. Basically, what you do is you are scoring internally each response, and you're picking the best one. And this is practically what best of n does. You ask for a model, like Isha mentioned, let's say 64 examples. So 64 solutions to some math problem. And then you use something called reward model, which is another language model, which is trained to do only one task, which is to grade these responses.
Right.
So the language model grades the response, and then you pick the best answer, and that's good. That's the answer you're going to present to the user. So on surface, it's like a very simple technique,
Right.
but it's sort of inefficient because you're generating like 64 full responses, and you're spending all the compute to generate them, but you're only picking one good one.
Right.
So you are generating wrong answers, which you can, if you're smart about it, you can trim it off before.
So are there any techniques today that leverage that insight that makes the search process a little bit more efficient?
Yes. So there's a technique called beam search. So let's look at what it does. So instead of generating a full response, what we're going to do now is break it down into steps. So let's go back to the math problem. So instead of generating a full solution to the math problem, what we're going to generate now is one step at a time. And we're going to generate multiple drafts. So let's say we generate M drafts for the first step. You pick only, like, say, top 3. And you're always going to keep expanding only the top 3. And how are you going to pick this top 3? You're going to use the reward model we talked about. So this, if you think about it, is more efficient than what we did with best of n, because you're only keeping the most promising responses, the top 3 most promising responses in this case.
So let me ask a question that. How do you know that you can trust the reward model?
That's a great question. These reward models are trained on some, let's say in this case, math data, but they're not always perfect. So reward models tend to make mistakes. It can only judge based on what it's trained on. So it's not universal. And this is where, hint, our method comes in. So we have a paper which tackles this particular problem, where we try to tackle this in a probabilistic manner, where we assume that the reward model is not perfect. So we introduce chance or randomness to this. So instead of picking the top 3 from the model, we're going to pick probabilistically and keep expanding those.
And so what sort of benefits do you see when you're switching to this probabilistic perspective on selecting these partial solution, if I may say?
So this way, we can keep answers which were seemingly wrong before, but they may evolve into the right ones.
Good.
So even though if you're evaluating the first few steps by the reward model, and the reward model might score it maybe not so great, but then eventually that might lead you to the right answer.
Right.
So through this probabilistic way, there is a chance that we keep these wrong answers in our memory and we are expanding them further. So the chances of you leading to the right answer is much more higher when you do this probabilistically than if you're picking the top ones.
Awesome. Thank you so much, Shiv. I know that Shiv broke the cardinal rule here of no, I think a few
heard the
times.
variable, but it's okay. You know, we can.
Probabilistic, I heard reward model, I heard M.
There was a variable.
It's a variable.
I heard
M.
variable.
I'm sorry.
It's okay.
Thank you very much for your response.
So let's dive back into this. I think we've talked about really interesting applications of inference time scaling, kind of using math as an example and these math questions. But let's say, I'm not in elementary school anymore and I'm now, an enterprise developer, I'm an enterprise leader. Why do I care? And how does this apply to me?
Oh, cool. This is a good question. Actually, I am super excited about inference time scaling because it unlocks the possibility of using small language models for the most difficult and demanding agentic tasks.
Yeah.
As you may know, AI agents have been a buzzword, mentioned by AI leaders Jensen Huang and Satya Nadella, because it represents one of the biggest market opportunities for AI deployment.
Yeah.
AI agents are basically programs capable of autonomously performing tasks through processes like self-planning and tool use. AI agents don't follow predefined steps. They can design their own procedures and follow it until it reaches solution. It's super cool, but it also places a high requirement on the precision and reliable decision-making ability of the underlying language models.
Yeah.
So previously, people thought that we have to go for the larger and frontier models in order to improve the accuracy of the agent system, but this also comes at a significant and recurring financial cost.
Yeah.
And inference time scaling is very cool because it reminds us that a small language model can do a lot more than what we previously thought. Shiv have previously given you an example of how small language model can outcompete large frontier model on math benchmarks, which is a very difficult and very demanding task. Small language model after inference scaling can beat frontier models orders of magnitudes bigger. And the similar phenomenon is also observed on coding tasks, which we care a lot about, that the small 14B language model after inference time scaling can outperform O1 preview level frontier models.
Wow.
Yeah, so for all those data points, for AI developers and enterprise leaders, I think the takeaway for us is that small models could match or exceed frontier model performance if they are given an inference time compute budget.
Yeah.
And if you are planning to build an AI agent system, if they are very complex as an end-to-end GitHub issue solver, or it's very simple as just a simple customer intent classification system, inference time scaling opens the door for you to use small in-house models to power your agentic applications.
Right.
And what this brings is full control and ownership of the agentic process, and also significantly lowering the recurring financial cost of your system.
These are the points I think in the beginning of the session,
Yeah.
you were really dialing down on.
Yeah.
Let me take a second to just also add something which I'm personally very passionate about. So if you look at some other verticals, right? So something that I'm very passionate about outside my main research is how can we bring generative AI into other domains of science,
Yeah.
engineering?
Yeah.
So if you take some examples, say engineering design or chip design.
Yeah.
these fields of science and engineering have sort of not benefited as much as, say, software engineering has. And in my opinion, that hurdle has been that of precision or lack thereof, right?
Sure.
Language models are inherently probabilistic, and their application to such domains, which requires a very high level of precision, is kind of tricky, right?
Yeah.
In my opinion. And I think this is one of the reasons why we have seen that segment of the industry relying on optimizers, search tools, and heuristics, simulators.
Yeah.
Tools that have sort of been meticulously calibrated to ensure the highest degree of precision.
Yeah.
Inference time scaling, I genuinely feel, I don't know if you agree with me, is going to change that game. I think it will, as we have sort of talked plenty of time here, this ability to leverage those tools that people have spent an enormous amount of research effort and development effort to create, so not throwing that away, not saying, no, remove this and bring in language models. It's a very collaborative, not so disruptive approach where you can plug in your AI system in a sort of seamless way, leverage the tools that the scientists and researchers and engineers have created in those domains to guide the search. And so I'm actually very, very excited about sort of the next era of democratization beyond just language and software engineering into the wider field of science and engineering.
Yeah, I think that makes a ton of sense. As we were kind of talking about in the beginning of this entire thing, the reason that I think inference time scaling is so interesting to a lot of people is that it brings the power of large language models, like GX was saying, to industries like we were talking about before, like healthcare and education, that have very regulated settings. But, as everyone knows, healthcare has been a topic of research for centuries, and people have spent their entire lives developing very, very precise research tools for it. So to kind of be able to harness those in the context of inference time scaling, I think really magnifies the impact that language models can have. And really, I think, is applicable to a wide variety of fields besides just healthcare and all these things. And yeah, I think it's going to be super impactful as we kind of dive into the next era of AI. So, at the beginning of this conversation, we touched upon this idea of reasoning and how inference time scaling connects to reasoning. And I think reasoning is, something that's been on everyone's minds nowadays with DeepSeek and all these new advancements that are coming out. How do these things connect and how do we think about them?
I love this question. I just want to say, I love this question. Inference time scaling versus reasoning.
Yeah.
I want to make a statement.
Go for it.
That I know how it will sound, but I think reasoning is a form of learned search. Kind of like advertising, inference time scaling. I'll let Kai expand on that. Just want to reiterate. I think in the long run, inference time scaling just has so much more promise. It's so generally applicable as we were talking about earlier.
Yeah.
Anyway, Kai.
Okay, thanks. So for between reasoning and inference time scaling, so our current understanding is that reasoning models, they learn to implement a certain type of inference time scaling strategies. By implementing, what we really mean that when the model speaks out the reasoning path, it's actually trying to kind of literally or verbalize a particular inference time scaling strategy. As you can see, those models usually say something like bad weight or trying to think backwards. And on top of that, they also trying to internalize a certain type of reward model that they usually use to kind of learn during their reinforcement learning phase, which I will also touch a bit.
Sort of like advertising the cost of running.
Yeah, basically.
Separate reward model.
Yeah, basically instead of using a program to run inference time scaling, they use the language model itself to run a similar type of inference time scaling. But it has both its benefit and limitations. I think the main benefit is that because everything is in a single model, like users or people who deploy such type of techniques, they don't need to worry about multiple models interacting with each other.
Load balancing and all that.
Yeah, they only need to worry about this one model. But on the other hand, I think the main limitation is that if we really want to push this reasoning capability in a particular domain, it's very hard to, let's say, in this domain, I have a particular verifier or a real model trend. If I really want to use it in a reasoning model, I have to somehow retrain this reasoning model so that it really pushes the limit of this reasoning capability in this particular domain.
Right.
On the other hand, if people using inference time scaling techniques, it's very easy to plug or even incrementally upgrade a particular verifier or reasoning model so to push the limit on this specific domain.
And that's why I kind of also agree with you that inference time scaling on the long run is probably the right path that to push into the industry, because people can have more specialized model, reward model, and this type of techniques. Another thing I mentioned a little bit was like how those reasoning models are currently trained. So far, those models learn to this type of reason or inference type scale through a reinforcement learning phase.
Right.
And it's actually like not a explicit way to teach the model to learn to inference time scale, in a sense that it kind of learns implicitly through a final outcome in the reinforcement learning. But if what the model really does is learn to search or learn to do an optimization procedure, we believe like kind of a more explicit way to teach model, like by actually synthetically generate data that in fact represents such process of search or optimization, might be more effective or more controllable. Because if we only rely on reinforcement learning, you might not expect what you want, or you might even have something unexpected. But
so you're saying that instead of letting the model figure out a particular inference time scaling or search method by how we train it in this reinforcement learning setup, you're suggesting that it might be worth exploring crafting synthetic data specific to a very particular known choice of search method, and then training the model to do that, like sort of a first principles approach.
Yes. Out of that, like I think a lot of people, including us, have found that it's, in fact, if you only rely on reinforcement learning, it also the base model you start with need to already see some type of those data to begin with. And the question is, if you are working with a model that haven't seen those data at all, how to even like bootstrap it?
That was a great answer, very comprehensive. You touched literally every part of it in detail. And yes, I agree with your insight that in the long run, inference time scaling might be the better path. Although I feel combining the two is ultimately going to be the best thing, because general reasoning skills is just going to be useful. It's going to make your model better, understand the domain, reason about the domain, having sort of like a common sense analogy there, like making the model have a common sense to reason about what it is doing will be right.
So you mean like inference time scale on top of a reasoning model?
Exactly.
Yeah. And you kind of touched on this also. Like, I think the great point you made is that inference time scaling is really cool, but now you can use this data to like go forward and make models better at reasoning. So there's like a very direct line between all the stuff we've been talking about and the capabilities that we're going towards. Thank you so much, everyone, for listening. As Akash mentioned at the beginning of this, our goal for this time was just to kind of provide an introduction to this overall topic of inference scaling and reasoning, and kind of chat about some of the work that we've been doing to explore those areas. We hope this helped to demystify some of the topics that have been, on everyone's minds nowadays, and kind of helped folks understand not only the topics themselves, but truly how powerful inference scaling can be and how many applications it has in a variety of enterprise areas. And help if folks employ them in their own workflows and their own applications. Thanks so much for listening, and we'll see you next time.
Thank you.